Section 2.2 is titled Describing Sets, and we're going to need to define what even that title means, because that word is a new word for us in this class, the word set. So that's actually where we're going to start. We're going to start talking about what in the world is a set. A set is simply a collection of objects. There it is. Any collection of objects is a set. So we can be talking about the objects being people. Okay, so you guys would be a set. You're the set of people who are currently taking number theory for elementary school teachers. We can talk about a set of objects truly being objects like the books on your bookshelf in your bedroom at home or something like that. Okay, so objects doesn't necessarily mean things. It wouldn't have to mean that. The elements are the individual objects in the set. So if we talk about you guys all being a set, then each one of you would be an element of the set. If we're talking about your bookshelf, each one of the books would be an element in that set. And when we describe sets, there are two basic ways that we can describe them. One is called the listing or the roster method, and then the other one's called the set builder notation. Now, the listing or roster method would work for the two descriptions I just gave you, right, where what you would do is we would just write down all of your names. We just list them, right? It's the roster of the class, like the class roster. So I could actually write down a list, and I write it, that's not a very good curly brace. Let me try that again. That's better. And I could actually put curly braces around the objects in the set. I'm going to give you another example that's got numbers in it so that I can show you what the other set looks like too. So a listing method might look something like this. Okay, so I'm just listing out the objects, listing out the elements. Set builder notation looks a little bit different. I'm going to write it down, and then I'm going to give you the language surrounding what it actually says. So for the moment, just write down what I've got, and then we'll talk about what it means. It's an N that looks like it has two lines on the left of it. When you see it in like typed form, it usually just looks like a really bold line on the left. So it kind of looks like that or something like that, you know, where it's really not that it's really all crazy sizes like that, but it looks really bold on the left when it's actually typed. But whenever we have it written, what you'll see is a double, like when we write it, we write a double line here, and then we do like this, and we cross over it. Okay? Okay, does everybody have that written down? Okay, we're going to come back to how I say that in just a second, but the next slide will actually have some of the notation on it for what we mean, so I'm going to flip to the next slide, and I'm going to write on that slide. All right, so a few of the notational items that you just saw in that particular line of writing is you saw a symbol that looks something like this. Yes? This symbol means is an element of. So like if we were talking about you guys, I could write something down that looks like this. I could put down Kaylee. I could put that symbol, element of, number theory class. Right? I think I missed an E. I think that the only Kaylee is that how you spell yours, Kaylee? Does anybody spell theirs that way? Oh, I got one of you. All right, fabulous. Oh, good. I mean, I had a 1 out of 3. There was 3 shots, right? I had 3 shots to get it right. Okay. All right, so we could write that kind of a statement. That E, it looks like an E, means is an element of. Okay? All right, another symbol that you saw used over there, and that's the one. This is the one that Caitlin asked me about, is the one that looked like an N with a double line on the left. This symbol is natural numbers. And we've mentioned this because it's come up a couple of times already, but natural numbers are the counting numbers. They're the ones that you start counting with when you're very small, and you always start with the number 1, and then you go 2, 3, 4, all the way until you stop remembering what number comes next. Right? That's what children do. Or maybe they get bored. I don't know. So that's natural numbers. If you sort of broaden your horizons a little bit, and you include in this list of numbers the number 0, that would be called the whole numbers. So same list of numbers, but you get to include the number 0 as well. If you decide that you can not only use positive numbers but also negative numbers, then you have something called the integers. And so that's my positives and my negatives. Like this. You might be looking at it and saying, okay, natural numbers N, whole numbers W, integers Z. It's Latin, so that's what the deal is with that, just so you know. It's Latin. And then rational numbers is the next one. It looks like a Q with an extra line on the left. This is rational numbers. And I'm going to define it a little bit loosely, but the basic idea of the rational numbers is that numbers that can be written as a fraction. So that's going to include decimals, repeating decimals. It doesn't include numbers like pi. Pi is not a rational number, because the expansion does not stop or repeat. But these are numbers that we can write as a fraction. Okay? So it also includes all the numbers listed above. Can I write the number 3 as a fraction? Yes, it would be 3 over 1, or at least that would be one version of it, right? So rational numbers include everything that is above it. So what we're doing as we move down is we're kind of making our picture of numbers bigger, in our mind. We're including more things. The last one that we're going to use for the purposes of this class is an R with a number on the left, or the double line on the left. Oh, I'm sorry, let me go back here for a second. You might have also wondered about rational numbers, why it's a Q. Does anyone know why it might be that way? Or have you heard before? What does ratio mean? Or what does fraction mean? What does it look like? What does a fraction look like? Something over something else, right? It's a number on top of something else. What does that business of being on top of actually mean? What is that operation? It's actually division, and it's coming from the word quotient. Who said quotient? Kaylee did? Okay. Yeah. So it's a division, and division has to do with the idea of being a quotient. Do you remember those things? Right? Sum and product and quotient, those kinds of things, right? Difference is the other one. Quotient. So the Q is actually coming from quotient. That's where that comes from. R. This one is the real numbers. And you might be thinking, well, aren't all numbers real? And the actual answer is, well, yes, but they aren't all classified as real numbers in the category. It's not a good title, but it's the title we have to live with nonetheless. Real numbers include everything above, okay? But they also include irrational numbers. So these are rational, everything above, we just said, and irrational. And we're not going to work too much with irrational numbers, but irrational numbers include things like pi and square root of 3, stuff like that. And there's another one. I'll write one more down. You may or may not have encountered it. E. E is actually also a number. It's about 2.78. Okay, so those kinds of numbers are actually irrational. They are real. There is a broader category. I guess you could say they're called complex numbers. Complex numbers include real things, and imaginary. So if any of you have seen the number I before, call it imaginary knot because it doesn't exist. Again, terrible, terrible language. But that's the term that's used to describe it. So there is something broader than we're talking about. But this is where we're going to stop. We're going to stop with real numbers. So let's go back over here now and identify a couple of things that we saw over here. Right here, this piece is now something that we have seen everything in. This says x is an element of the natural numbers. So that means that x is things like 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay? That's what x is by that argument. This argument says that x is greater than or equal to 7, right? So x is not 1. X is not 4. And then let me actually read this now from left to right. You can write this down as I read it. What this notation actually says is x, this bar, such that. So these are the values of x, such that x is greater than or equal to 7, and x is, or is an element of, the real number, the natural number system. Now, the reality is, these two descriptions are just two descriptions of the same thing, right? Isn't that what that list above is? Natural numbers, bigger than or equal to 7. All right, we're going to use some of this notation. Do an example here. Yeah, example number 1. Absolutely. Okay, so let's take a look. This one says that we're going to write the set of all numbers less than 5 using, number 1, the listing or roster method, and number 2, set builder notation. So I need to use the set builder, let me make a note that both of them use curly braces, right? So the first thing I'm going to do is I'm going to draw my curly brace one to start. And then it says the listing or roster method, and I'm supposed to be listing or writing a roster of all of the numbers that are less than 5. Okay, so where do I start? That's set builder notation. I'm just doing a listing method first. 5? 4? Okay, if you prefer. I've taught this course lots of times, and I don't think anybody's ever put them in that order for me. You guys are so much fun. Typically, this is what I have people tell me. Of course, they're identical. They're the same thing. It doesn't make any difference. But this is a list of all of the numbers, natural numbers, that are less than 5, right? Does that work? Sure. That's the listing or roster method, okay? The second one says to put this in set builder notation. So, Amanda, you were trying to tell me what set builder notation was. What would it start with? X. Yep, you're going to do an X and you're going to do a bar. It's always going to start like that, okay? And then the other two pieces that we're going to put in here actually could go in any order. There are two things that I have to identify. I have to make sure that I'm talking about, and this is not worded well. I'm sure that was a typo. Does yours say natural on your paper or does it not? Okay, put the word natural in there. I know that was left out. It has to be in there. It's not going to make any sense. Set of all natural numbers, all right. So somehow in my listing method, or my roster method down here, I said the wrong thing twice, the set builder notation method down here, I have to include a fact that says these are natural numbers. That's one of the facts I have to include. The other fact that I have to include is I have to include the fact that it's less than 5. And again, I can do each of those things in either order. So I'm going to do them in the order that they're kind of in the directions, just so that you can see that I can do it backwards of the way I did it before. So the first thing I'm going to write down is that x is a natural number. So x is an element of the natural numbers. The next thing I need to do is I need to say that x is less than 5. So what does that look like? X, and I have that less than symbol, right? And I've got my number 5, and I can close it off. Any questions on that one? Okay. A couple other things. I actually made a comment just a moment ago that these two on number A, or letter A here, are the same, right? They're actually something called equal sets. It's the very first one listed here. Equal sets are two sets that contain exactly the same elements. And it almost feels like it's silly that I even wrote it down. Because if I asked you what equal sets were, that's probably what you would have told me anyway, right? Sets that have the same stuff in them, that would be equal. All right, one-to-one correspondence is a pairing of elements between two sets such that each element of one set is paired with exactly one element of another set. So imagine, and I'm going to do a real straightforward one. Let me do it this way, actually. So I've got a collection, a set of 3 objects, A, B, C. And I have a collection over here of a set of 3 objects, 1, 2, 3. And a one-to-one correspondence says I have the ability to pair these up so that each one has a partner. Everyone has exactly one partner. Nobody's duplicated, nobody's left out. Okay, one-to-one correspondence. This is what my children want to have happen when we invite people over for dinner, right? Everybody wants a buddy. Nobody left out. Nobody wants to share their buddy either. So we got to try to find the same number of buddies. All right. The reason this is coming up is because we have another statement down here that says equivalent sets. And probably if I'd asked you before class, equal, equivalent, do they mean the same thing? You would have said, yeah. I mean, equal and equivalent, they sound the same, right? Well, in terms of set notation and what we're doing, they mean something slightly different. Equivalent sets are 2 sets for which there exists a one-to-one correspondence between the sets, i.e., the sets have the same number of elements. How is that different from the first one? I mean, 2 sets that contain exactly the same elements, they have the same number of elements. What's different? Nope, it's not about the pairing. They both have the ability to be paired. What's different in the definitions, guys?
2 sets.
Well, both of them have 2 sets.
Equal sets have exactly the same elements.
Right.
And the other one doesn't say exact.
What does it say they are instead?
Just the same. Oh, and the one close.
Just the same number of them, right? This is why I wrote this down here. They have the same number of elements. Same number. And this one up here says exactly the same elements. Right? So like my picture right here that I just wrote down, these would be equivalent sets. Yes? Are they equal sets? No. Because they would have to have actually the exact same items in them to be equal. Are you with me? Everybody good with that notation? Okay. So as long as they have the same number of items, they're equivalent, but they are not equal. Or they don't have to be equal. Okay, let's do an example dealing with the one-to-one correspondence issue. All right, so the question asks, how many one-to-one correspondences are there between 2 sets with 6 elements? Okay, so visually, let me just draw you what we've got, and you can see what I'm not going to continue the picture. I'm just going to draw the picture to start with. So I have A, B, C, D, E, and F. That's 6 elements. And then I've got 1, 2, 3, 4, 5, and 6. Okay, so do I have the ability to make a one-to-one correspondence? Yes, because there's the same number of elements. I do have the ability to do that. So let's take A for a moment, and let's just ask, how many different pairings could we make with the letter A? 6, right? Because there's 6 numbers. Each of the ones could go with the number 6, or could go with the letter A. Are you with me? So I could do a pairing. Any of these would be a possible pairing for the letter A. So my letter A had 6 possible pairings. But once I have paired letter A up with a value on the other side, once I've done that pairing, I'm ready to do letter B. How many pairings now could letter B have?
5.
Only 5. Why?
Because A is already with one.
Yeah, A is already taken with someone else. I mean, like we already paired him up. So now I've got letter A, they've got a partner. Letter B has a partner. How many options does letter C have? 4. There's only 4 numbers left. How about letter D? 3. And letter E? 2. And then what happens to lonely little F? He's the last one to get picked, right? Or the last one to get a partner. Okay, so what are we going to do with this 6, 5, 4, 3, 2, 1? Any ideas? Good guess? We're going to multiply them, yeah. And what this is actually doing is, and it's not actually written on my notes in here. Let me do it, and then I'll tell you. All right, so we're going to multiply them. We're going to do 6 times 5 times 4 times 3 times 2 times 1. And what are we going to get? Yeah, 720. In a later section, we actually give this a name. There's 720 correspondences. This is called the fundamental principle of counting. Fundamental principle of counting says that if you have so many ways that one thing can happen, followed by so many ways something else can happen, the way that you find out how many ways it all can happen together is you multiply the results. That's what the fundamental principle of counting is. So that's what you're actually seeing happen right here. Okay? 6 times 5 times 4 all the way down. For those of you who have taken what we would have called elementary math 2, do you remember another way that you could write 6 times 5 times 4, all that down? Do you remember it? It's a factorial, yeah. So if you haven't heard or seen factorials in a while or whatever, just ignore me for the moment because we're not getting into them here. But that is 6 factorial. So, okay, a couple other things notationally that we need to be aware of. Cardinal number. Cardinal number is just the number of elements in the set. And if the set is S, then we write the cardinal number as N parenthesis S. This is the number of items in set S. So if I talk about my family as set S, then the number of people in my family would be 6. So the cardinal number for my family is 6. The cardinal number for our classroom is, I think it's 17. I think. I may be wrong. Maybe you guys are all here and it's 15. I don't know. I can't remember now. But whatever. It's the number of people in the class, right? Okay, finite set. A finite set is a set for which the cardinal number is a whole number. In other words, you have the ability to count them. Okay? It might be a really, really big, large number, 10,000, 2 million, 322 trillion, I don't know, but it has a number that you can associate with it. That's finite. Infinite. Infinite set is a set where the cardinal number is not a whole number. Right? So this would be something like the number of stars in the universe, the number of sand on the seashore. Right? Remember that conversation that Abraham and God had? Talking about that? Right? We're talking about something that's infinite, at least in terms of what we can conceive ourselves. If you were talking about listing out the set of all natural numbers, that'd be infinite because it never stops, right? So that's what you're talking about there. All right, another one. This is a fun one. The empty or null set. So empty and null are used interchangeably there. So sometimes you'll hear it called the empty set. Sometimes you'll hear it called the null set. This is a set that contains no elements. It has a cardinality of 0, and it is written in one of 2 ways. One way that you write it is like this. It's like a 0 with a slash through it. So this is part of why I cringe anytime somebody writes their zeros with slashes through them, because there's other notation that actually means something. Okay, so it means empty set. It also has another meaning in mathematics. Where have you seen this used before for another meaning? Do you remember? What?
I know I've seen it, I just can't remember what it is.
It's okay. You'll see it used sometimes in mathematics for the phrase no solution. If something doesn't have a solution, you get a 0 with a slash through it. For set notation, which is what we're using it for, it means the empty or null set. Okay? There's one other notation that can be used here. You can write empty parentheses. Right? Parentheses with nothing in them. And what you cannot write is you cannot write the 0 with a slash through it inside of the curly braces that should have been empty. You can't combine these 2 notations. That is not appropriate. Okay? It's one of them or the other one of them. All right, so an empty or a null set. You always give an example, an empty set. I used to give the example of the teenagers that live in my house. That is not an empty set anymore. as of about a year and a half ago was. So now I can give you the set of the babies that live in my house. That is the empty set. There's none. Even though some of my children think there should be more, there's none. We're done. Six people in the house is enough. All right, so empty set. All right, so just think down for a second. I want you to write something down for me. Think about your life, some context, something, whatever, and write down something that is an empty set, something that you can describe that has nothing inside of it. Okay, take like 30 seconds. I want you to write down something in your life or in your surroundings or whatever that is an empty set. Okay, I want 3 people who are willing to give us their examples. Someone share.
The number of times I've been overseas.
That's a great example. Now, so this would be something like where you probably wouldn't say number of times. You'd probably say something like trips overseas, right? And the number would be 0. The cardinal number for trips, the trips you've taken overseas would be 0. Okay, what else? What do you have, Kaylee?
How many older siblings I have?
Oh, very good. Okay, so older siblings. Kaylee's older siblings. And it would be an empty set. All right, one more. Tasha.
Short people in my house.
Short people in your house. Fantastic. Wonderful. Okay, good examples, good examples. So we can all describe something where there's just nothing inside of it, right? Okay. All right, let's take a look then at finding cardinal numbers of things that do have stuff inside of them. All right, take a look at this first one. We've got the numbers from 9 up to 99. And we want to know the cardinal number of this set, which starts to feel like we've done something like this before, haven't we? All right, so how are we going to find the number of items in these sets? 99 minus 8. And why are we minusing 8 instead of 9? Do you remember? Because we need to include 9 in the numbers that we're counting, right? So we list the numbers, we subtract off the numbers that come before 9. All right, so 99 minus 8 would be 91. Okay, how about the next one? What do you think?
You have to divide it by 2 and then subtract what? When you do it, you do it on the first one, but you also have to divide it by 2 because it's every other number.
Okay, so good thing to notice, this is every other number, right? And it doesn't matter whether it's evens or odds. In this case, it happens to be evens, but it is every other number. We actually get to avoid the subtracting on this issue. Do you know why? Yeah, because if you're actually listing all the numbers from 1 up and then you threw away the odd ones, you'd get everything that you have left here. So yes, you would be subtracting, but you'd actually be subtracting starting at 0. So in some sense, we don't have to subtract anything because the even number that comes before the one we're on is 0. So we do end up with just taking the 2002, divide by 2, which gives me 1001. Nice. All right, the last two are written in such a way that you have to really think about what in the world is the set. So it might be helpful as you're looking at it to write down what the set actually is in listing method if you're having trouble looking at it and thinking about what the heck is it talking about. Okay? So let's actually try that on this first one. This first one says that we're going to have all of the numbers that are x squared when x is the numbers 1, 3, 7, all the way up to 99. Okay? So I know you can square numbers, but basically I want to show you is that all they're telling you to do is to do 1 squared, 3 squared, 7 squared, all the way up to 99 squared. Everybody with me on that? That's all this set is the squares of these odd numbers. So the question then is, how many of these are there? Amanda? Oh, it shouldn't have. You're right. It does skip 5. This is this is the problem when I create a new course, is that there's typos in all my stuff. So you guys should have waited to take this till spring. It'll be perfect in spring. There will be no typos. It'll be fabulous. Thank you for catching that. I appreciate it. All right, everybody get that 5 squared in there. It should be there. That is not supposed to have been omitted. Thank you. It's supposed to be all the odd numbers. Okay? Yeah. All right, so taking a look at this, 1, 3, 5, 7, 99, up to 99. How many of these are there? 45? 49? What do you think? Actually, I think they're 50. Okay, so on the second one, on part B, when we looked at the even numbers, we had this issue where we said if we started with 1 and we went all the way up to 2002, we'd have all the numbers, 2002 of them, right? But then we had to throw away the odd ones. You guys with me? Okay, so we ended up with 1001. Well, down here, well, you know what, let me just make this first comment, is, do the square matter? No, the square has nothing to do with how many of them there are, right? So counting this list that I wrote out here is the same as counting the list that I was originally given. Agreed? Yeah? Okay, good. All right, so let's think about that list. That list is just odd numbers, right? So if we start at the number 1 and we went all the way up to the number 100, how many numbers would we have? We'd have 100. And then I'm going to throw away the evens. So I throw away the 100 as well. Are you with me? That's what's happening there. I mean, like, you could physically sit here and count them if you're concerned about it. But really, that's what's happening, is I know I'm throwing away evens. So I'm going to go from something that's, from the beginning, 1, all the way up to something that's going to be an even number, so that when I divide them, it makes sense. So there really are 100 numbers, and I'm throwing away half of the evens. So I get the 50 that are left. It looks funny, but it still works. How about D? This one's even weirder looking. X such that x equals x plus 1. It says x is a natural number. Look, the notation, this computer program puts the double line in the middle of the n. You guys notice that? That's a little different, but let's write out a list. What numbers work in this equation? That is, what number works in the equation x equals x plus 1? It is. Why, Amanda?
Because nothing equals that same thing plus 1.
Yeah, nothing equals itself plus 1. And I don't mean the number 0. I mean there isn't a value that works here, right? There is no value that is itself plus 1. This actually looks a lot like that example that you guys did in your homework last time, doesn't it? Where it said n plus 1 on one side and n plus 3 on the other or something like that. And we're like, wait a minute, that's not even possible. It doesn't work. And that's the example here too. There's nothing in this set. It is the empty set. So what's its cardinality? That is, how many items are in it? 0. Right? The empty set. This is really terrible notation. Let me move this. I did it up here too. I did it twice. The cardinalities are these numbers. The sets are not these numbers. The sets have actual items in them. Okay. I had avoided those Euler diagrams before. You know, I did the one that I had said that I inadvertently had a problem in, not because they're complicated, because we're going to take a variety of that in this section and look a little bit differently at them. We're going to look at what are called Venn diagrams. They're related to Euler diagrams, but they're used a little differently. Venn diagrams are diagrams used to illustrate ideas in logic. And illustrate really means like we're going to draw a picture. It actually does mean that. So illustrate as in show and illustrate as in draw a picture. A universal set is a set that contains all elements being considered in a discussion. So a universal set is usually something that's broad, right? So like if I was talking about a universal set related to OBU, I might be talking about all of the women in OBU. Or I might be talking about all of the students at OBU. Okay, something is usually a broad description of something. And then a complement is the opposite of a set being discussed. So let's say, for instance, that I was talking about all of the students at OBU as my universal set, And then I was talking about a smaller collection of that, which is all the females. What would the complement be? What's the opposite? All the males. Okay, that's all complement is. Complement is given an object, or not object, but given a smaller collection called a set. This is all the elements in the universal set that are not in set F. So let me show you with a picture what this actually looks like. I need to give you one notation first here. It's written F with a bar on the top, horizontal bar on the top of it. Okay, so let me just give you a real quick little picture of this. Okay, so a Venn diagram looks like a box with circles inside. That's all it looks like, a box with circles inside. The box is the universal set U. The circle is a set, and in this particular discussion they called it F. Okay, so F, and then I was using it for females. So if U is all of the OBU students and the red circle F is the females, then the part on the outside of F, still inside the box, but outside F would be the males at OBU, right? So outside here, this area right here would be the F complement, which we understand as being males in this discussion. I'm going to use another OBU example in my actual example next, okay? But a similar idea. This will be our last example for today. If U is the set of all students at OBU, okay, that's the U I just used, and A is the set of those who are graduating, describe the complement of A. What would the complement of A be? Yeah. Now we still want them to be OBU students, right? So these are OBU students who are not graduating. In some sense, this is kind of like when we did negations, right? We put that word not inside of there and we changed the meaning. It's the same thing for complement. It's just exactly what is opposite of the description. It still has to be inside of whatever category we're looking at, right? So this is not the faculty members. This is not the high school students or somebody who's at Seminole. This still has to be OBU students, but in this case, it's OBU students who are not graduating. Okay? Everybody good? All right.